Well, I guess we'll get started and see if anybody else shows up. Um, it's all right. It'll be recorded anyway. Um, so yeah, well, not too much in depth, at least for these first few slides, but we'll kind of start getting into some more detail on the next slide deck, chapter 5 of the PAC. But first, we're just going to go over some basic principles of flight, and then we'll get into the actual uh, physics and like some extra fun stuff. But to go over just some basic stuff, we'll start with these. So yeah, the physics of the air. So I mean, the air is obviously a fluid, and so it has viscosity and has friction, and so these principles of the air allows us to say some things about what the aircraft will do during, say a hot day or humid day or whatever. Um, the air, if it's really hot out, really humid out, is going to be a lot harder to move through, or actually not going to be hard to move through. It's going to become less efficient for the aircraft. It's a lot harder for an aircraft to create the lift that it needs to fly, and it likes colder air. Colder is a lot more dense, and so that allows the aircraft to perform a lot better. Um, but the air also has this certain amount of friction, and so your climb rate and your overall lifting performance and stuff will change based on what the air is doing, whether it's really viscous, or whether it's not, whether it has a lot of friction or whatever. So but that's more related to weather stuff. But just to reiterate, that about the air. So again, we've talked about standard pressure and stuff, but standard pressure is 29.92 inches of mercury, or 13.2 millibars, or 14.7 psi. And then the temperature is going to be 15 Celsius or 59 degrees Fahrenheit. And we've talked also about the standard lapse rate, which is the decrease in temperature as altitude increases. So generally, as altitude increases for every 1,000 feet, we decrease by 2 degrees Celsius. And then we also decrease the pressure by an inch of mercury per 1,000 feet. So that's just kind of our standard um, numbers that we use for calculating things like cloud height, and um, some of the other general performance stuff is based off of this standard. So pressure altitude, I'm not sure if we've actually given a formal definition to this, but pressure altitude is the height above a standard datum plane, which is the theoretical level where the weight of the atmosphere is exactly 29.92 inches, the standard pressure, and as measured by a barometer. So this is the point at which the atmosphere is this standard value, this 29.92 inches. And we use this in a lot of things. We use it in determining our aircraft performance. So when we go and we calculate our pressure or the our density altitude, we use pressure altitude to kind of set this baseline, and we use it for some practical applications as well. So when you get to flight level 180, everybody sets their altimeter to 29.92, just to make sure that everybody's on the same page, because after you get that high, you're not so much worried about where the ground is at as much as where other airplanes are at. And so having that standard is good. So everybody above flight level 180, which is class Alpha Airspace, they are all on 29.92 inches of mercury for their altitude. Yeah, and to get pressure altitude, you just set your altimeter 29.92, and it'll tell you what your altitude is, given that standard pressure. Density altitude is a number that is more helpful this is how the airplane is going to actually perform. So instead of having this number, which is just the standard, we now have this pressure that is more relative to what we're feeling. So this affects aircraft performance a lot more. And this is what we calculate and use for takeoff performance and landing performance and stuff like that. So density altitude is the vertical distance above sea level and the standard atmosphere at which a given density is to be found. So we'll look at a chart on the next page, but basically it's just this correction based on what the airplane feels like. So just another anecdotal note about this is that as the air becomes less dense, basically your performance decreases, and as it becomes more dense, your performance increases. So during the summer, you have less performance than you do in the winter. Winter flying is a lot more fun because you can take off at crazy rates of climb and stuff, whereas in the summer it takes forever and it's really sluggish. So here's this chart I was talking about, and this is how we calculate the density altitude. Alternatively, you could just use this formula. So you take your pressure altitude and you add it to this this conversion here. So you have 120 times your outside air temperature, and then you subtract your outside air temperature from this ISA value. And basically, you can then calculate your density altitude. But oftentimes for like the FAA exam and stuff, you'll just be given a chart like this. There are calculators that have this formula in it, but I wouldn't worry about memorizing it. Just know that's where this density altitude chart comes from. So yeah, so to calculate your density altitude, just take your outside air temperature, which is this bottom part of the chart, and you can be either in Celsius or Fahrenheit. For this, they've allowed us to convert it here. So, if you take, let's say it's 60 degrees outside, so we go down, we find 60 degrees Fahrenheit. And then we take our density altitude, and you could find the pressure altitude. Or you could find your density altitude if you knew your pressure altitude. So this chart works both ways. If we want to find our density altitude, because oftentimes we'll know our pressure altitude and not our density altitude, what we'll do is we'll have to go over to the side here, the sidebar, and we'll have to calculate it based on our altimeter settings. So if we look at the METAR, and the METAR says that the altimeter setting is, 30.0. So it's a little bit above the standard pressure. We'll go over to this chart and we'll look for 30.0 on the left side, and we'll go over and we'll find the conversion factor. So the conversion factor for 30 millibars or 30 inches of mercury is going to be minus 73. And so we'll take this number, this minus 73, and we'll subtract it from whatever our altitude would be. So then we can go up here and we can then put in our pressure altitude. So I don't know, whatever that is, let's pick an easy number. So 6,000 feet. So 60 degrees Fahrenheit at 6,000 feet. And you can go up here and you can find where it intersects. And so the line intersects right here, and then you can just go over and you can read your density altitude. So given the 60 degrees and given the 30.0 altimeter setting, for some reason that gave us 6,000 feet for our pressure altitude. And then we can just go over here and say that, okay, based on that, we can say the density altitude is going to be about 7,100 to 7,200 feet. And so that's almost 1,200 feet above where, our pressure altitude said we are. And so that's quite a bit. And that just goes to show you that, this increase in temperature and increase in pressure can cause this great increase in what the airplane actually feels like it's at. So it feels like it's a lot higher than it actually is. So hopefully that makes sense. Whoops. That's just something to keep in mind, and you'll probably see this come up again down the road. So just keep that in the back of your minds. But it'll be easier once we actually apply it in like flight calculations and stuff. So effects on air density. So a few things can affect air density. So pressure is one, and then the other two here, temperature and humidity, we kind of talked about a little bit, but we'll go over them in a little bit more detail. So pressure, obviously, when it changes, the air is either increasing it's either expanding or contracting, I should say. And so as you expand the air, it gets less dense, and as you contract the air, it gets more dense. And so this change can change how the airplane performs. So dense air, like in the winter, when the pressure is going to be lower. It's not necessarily lower in the winter, but when it's colder out, this air is a lot closer together, and so your density would increase, and so you get much better performance from that. So low pressure system moves through the area, your pressure is going to decrease, and so your air becomes more dense, and that would increase your performance. Now I wouldn't recommend go fly. Usually low pressures bring pretty bad weather, so I wouldn't necessarily go recommend you go fly in that, but that's just an example. So temperature usually has another large impact on this. So as temperature increases, the air density decreases, and when it decreases, the density increases. So cold weather, better for flying. So a low pressure, cold weather day, that's going to be your best day to fly. So and lastly, humidity. Humidity isn't as big of a factor. It does affect it, but just not as much as the other two. So generally as humidity increases, the performance generally decreases, but it doesn't really affect the performance as much as temperature and pressure do. So a jump in humidity from like 30 to 80%, you probably wouldn't notice it as much as a increase of like 10 degrees or a pressure increase of 0.5 inches or something. So all right, now that we have talked a little bit about air density and factors that impact that, we're going to talk about now the theories of lift, and then eventually we'll talk about the four forces of flight again in more detail and some other stuff. So aircraft produce lift to fly. I guess that should be kind of obvious by now. And there's two ways to do it, or at least there's two theories surrounding this. So the first theory is Newton's laws. So specifically Newton's third law we're talking about here. That's for every action, there's an equal and opposite reaction. So the air hits the wing, and it causes the airplane, to have this opposite reaction, and it causes it to fly, I guess you could say. And that is true. That does happen. However, at least in aircraft that are conventionally designed with propellers and jet engines and stuff, this doesn't really impact the overall lift capability. In some smaller aircraft, specifically like RC and stuff, this is a big thing, especially for very light RC aircraft that have a really crazy high thrust to weight ratio. They don't need to create lift because their thrust is so high, and they can basically do whatever they want. And so because they don't need to create this lift, they can just create this Newton's third law. And so oftentimes smaller aircraft like that will not even have a camber to their wings. They'll just be this rectangular box that is just pushing against the air in order to provide some aerodynamic stability. So so that's Newton's third law. But the main way the aircraft produce lift is through this Bernoulli's principle. I'm not sure if you've heard of this before, but we're just going to go through it really quick. So basically, Bernoulli's principle is that as a fluid's velocity increases, it becomes less dense. And this is important because the aircraft's wing is designed in such a way that it will take advantage of this increase in velocity in order to create a decrease in pressure. So as you can see here, we have this tube where in the middle, it contracts to a smaller diameter than it is on the outside. And so the air coming in has to increase velocity in order to get through the tube. And that causes this decrease in pressure. So we can see coming in, we have a, I don't know, whatever this 5 is in velocity, meters per second or feet per second or whatever that is. So it's coming in at that, and then the pressure is this constant as well. And as we get here in the middle, the velocity increases to like 7, and the pressure decreases to like 3. And then as it expands back out again, the velocity goes back to normal, and then the pressure increases again. And so aircraft take advantage of this through the airfoil design. So airfoils have a lot of different shapes, but in general, the top will be a further distance to travel than the bottom. So you have this arc on top, and then on the bottom, it will usually be flat, except for a couple of different designs that don't do that. But in general, most light aircraft and most commercial aircraft as well will have this kind of arcing design on top and this flat bottom. And so what this does is the air has to travel much further over the top than it does at the bottom. And so the bottom doesn't really increase in velocity. In fact, relative to the top of the wing, it increases in its density. And as the air travels across the top, it has to increase in velocity in order to cover the same distance in the same amount of time. And it causes this decrease in density. And so this pressure difference, the decreased density on top and this relative increase on the bottom, causes the creation of lift. And so that's why the wing is shaped the way it is. You can kind of see this progression of the wing shapes from the early days to now the supersonic airfoil design. But most aircraft nowadays, if you go out and look like a Cessna or something, will have this Clark Y airfoil shape. That's a pretty classic one. Some other aircraft like fighter or early fighter jets like the P-51 and stuff like that, they'll have this circular airfoil design, and that just helps, or this laminar flow one as well, and that helps with maneuverability in any flight attitude. So basically they can be upside down and they'll be producing the same amount of lift as if they were right side up. And so they'll have this kind of symmetrical airfoil design, whereas lighter aircraft and commercial aircraft will have this flat bottom on their aircraft. So and we kind of talked about parts of a wing last time, but there are some invisible parts as well that we didn't really talk about. And the main one that you'll have to remember is this chord line. So the chord line is an invisible line that runs from the leading edge of the wing to the trailing edge of the wing. And this is used just kind of as a reference point when we're talking about what our angle of attack is. And so the angle of attack is the angle at which we have this chord line intersecting the relative wind. And we'll talk more about what that means in the next section here. But just for now, just remember that this chord line is this invisible line that runs from leading edge to trailing edge of the wing. All right, so we talked about the physics here, but this is kind of these pictures here just kind of show a better illustration what we're talking about with like the angle of attack and stuff. But don't worry about that too much right now. So you can see on the top here we have this increase in lift at the center of pressure, which is our invisible lifting point or the maximal lifting point of the wing. And then on the bottom we have this this pressure that is exerting back up. So it's kind of keeping the wing there in place. So So we have this creation of lift that's caused by this decrease in pressure on the top and this relative increase on the bottom. And there are some side effects. The main one that we're going to talk about is this wingtip vortice. And the wingtip vortice is especially dangerous if it is caused by larger aircraft. You can kind of see this picture here, kind of illustrating this by this jet flying through clouds. We get these swirling patterns off the tips of the wings. And we will talk more in depth about why these are created in the next slide deck here. So I'm not going to go too much into it. Just know that that these exist, and they're caused by the creation of lift. So here I just have a video that kind of illustrates this angle of attack idea, and also kind of shows the flow of air over the wing surface. So this video, basically what they did is they took a model of an airfoil, or a cross section of an airfoil, and they put it in this this thing of air, and they're shooting these lines to help kind of show us the airflow, these smoke trails or whatever. And if I just play it here, we can see that as the wing increases in its angle of attack, so as this wing starts to go up, the air at the top here starts to separate more and more, and it's less smooth. And eventually, this air at the top can't hold on to the wing at all. And we'll see here in a second, hopefully, they'll show us the stall point. So we'll see as we see here, it's kind of very smooth, it's sticking to the wing. But as we increase this angle of attack, or this angle between relative wind, we can see that it starts to separate back here and eventually reach a point where it can no longer stick to the wing at all, and we lose all that right there, that creation of lift, and we just have this air pocket back here. And this is the point at which the aircraft is stalled. And so there's no creation of lift, and the wing is useless at that point. It's just sticking out there. So we have to then dip the nose back down to re-engage that flow over the wing, and then we can start producing lift again, and we can start flying. So I'm going to stop that there. So yeah, hopefully I explained that sort of okay. But just know that the angle of attack is this angle between the chord line and the relative wind. So in the case of this video, you have the chord line here and the relative wind, which is this stuff. And that angle determines how much lift you can produce. So, and eventually you'll get to a point called the critical angle of attack, which we saw, where the airflow completely separates from the wing and you lose the creation of lift. And so that's kind of the key term that you'll need to remember, is the critical angle of attack, which is the point at which the wing stalls. That's irregardless of how fast you're going. It's just a number that exists. So, all right, hopefully that makes sense. Any questions about that?
I think so.
Okay, cool. Well, if you think about it, the next section's pretty much the same stuff, so we'll get into that here. We're just going to go a little bit more in depth with it. So let me pop that on there. All right.
What does velocity have to do with stalling then, if anything?
Yeah, I mean, not really much, except for the fact that usually, you're not going to stall the aircraft at a really high velocity, if that makes sense, because you won't reach that critical angle of attack probably going like 100 knots or something. You can, but you'd balloon up. You'd gain like 500 feet or 1,000 feet a minute if you tried to reach that critical angle of attack. And so you reach that critical angle of attack usually when you're going much slower. So there is a stall speed in the aircraft, and for like a smaller aircraft, it'd be like, I don't know, 45 knots or something. And that stall speed is usually around the point where if you tried to lift off the ground, or if you were flying and you reach that speed, your aircraft doesn't have enough forward velocity to keep the air flowing over the wings. So that critical angle of attack is reached and the airflow stops, and then you stall. If that makes sense.
So it's sort of two different ways to separate the airflow from the wing.
Yeah. So I mean, you're reaching the critical angle of attack in both phases of flight, but it's this angle at which, I guess it's two different ways to get to it, kind of, but you're probably not going to reach it going 100 knots, if that makes sense. At least in normal flight.
Turn into a rocket ship before you get there.
Yeah. And then eventually you will slow down to the point where you stop producing that lift. So yeah. Hopefully that makes a little bit more sense. But it's this usually you'll see it associated with that stall speed, even though it is an angle. But this is kind of a side note, but some aircraft do have angle of attack indicators, and a lot of people actually don't really know how to use them. Our flight school had them, but they never really taught us how to use the angle of attack indicator, and they're really helpful because they show you how close you are to that point of stalling, and they base it off a lot of factors, and so they're kind of cool. But yeah, anyway. So we're going to go a little bit more in depth now with the aerodynamics of flight. So we're going to return to the four forces of flight, and we're going to talk about them each more in depth. So hopefully we should get a better understanding of drag, especially, or we'll talk about all of them, but there's a few that are a little bit more in depth. So four forces of flight are lift, weight, thrust, and drag. And so we have this lift component, which is created by the wings. We just talked about that. It's created by Bernoulli's principle. And that counteracts the force of weight, which is the pull of aircraft from the earth. And, this can change with how much you load the aircraft with people, baggage, fuel, whatever that might be. Then you have this thrust force, which will cause the aircraft to move forward through the air. It counteracts the drag force. And then finally, we have this, the drag force, which is caused by the interaction of your aircraft with the air. And we're going to go pretty in depth with that here. So first off, lift. Lift is caused by the air moving over the surface of your wing. So as soon as you don't have that, your airplane does not produce lift, and it is stalled. The pilot can control the amount of lift produced by changing the angle of attack. And so as we can see in this diagram here at the bottom, you normally at a high speed will be pretty level because your aircraft doesn't need to produce, your aircraft is efficiently producing lift. And so once you start to slow down, at like a cruise speed or something, you have to increase that angle in order to produce the same amount of lift. And then eventually, once you get to a really slow speed, close to your stall speed, you'll have to increase this angle even more in order to produce the same amount of lift and to stay flying. And so you're kind of trying to force this air around the wing to create this lift that you need to fly. And this is where you get into a dangerous spot down here, is where your angle of attack is increasing to the point where it reaches the critical angle of attack. And so I think this might help clear up some of the questions about this, that, normally when you're flying really fast, you're producing lift very efficiently. And as you slow down, this is when you start to get into dangerous territory, where you need this wing at this high angle in order to produce the same amount of lift. And that's where people get into trouble, especially on landing, sometimes on takeoff as well, but on landing, especially where they're getting really close to the runway and they keep pulling back and they're pulling back, trying to get to the runway, when in reality, you shouldn't be pulling back because although you are creating more lift, you only create so much lift. And then once you get to the point where you can't create any more lift, the airplane stalls. And so instead of pulling back on the yoke when you're landing, we actually do the opposite. We actually push down. And the way to counteract the loss of lift is to increase your airspeed. And so you use the throttle to increase your airspeed, and then you lower the nose to increase the lift. And so, yeah, we talked about what AOA is. So angle of the chord line and the relative wind. So lift, more formally defined, is this value, this value here. So we have this formula. So the center of lift, which is the CL, or not the center of lift, the coefficient of lift, I should say. And this is a number that is calculated by the manufacturer of the wing. And this number is done by, mathematical computation on the wing's structure and a whole bunch of numbers and stuff. Anyway, sometimes they publish this. Sometimes you have to go digging for it, whatever. Just a number that exists. And yeah, so this coefficient of lift value, you use this and then you multiply it by the rho, which is air density, times the velocity squared, and then you multiply it by the overall surface of the wing. Then you divide it by 2. So this lifting component changes. It's proportional to the air density. So as air density increases, your lift increases. Does that make sense? It gets colder out, your aircraft is going to produce more lift. So that's good. If the air density increases, high pressure system, good. Then your aircraft performance will increase as well. So besides that, though, your velocity is squared here. So this is exponentially related to your total lift. So as your velocity goes up by 1, it's actually going up that squared, or maybe 1 isn't a good number, but 2, it's actually going up by 4. So this airfoil velocity, so as your velocity increases, it exponentially increases your amount of lift that you're creating. So that's a good. And then your surface area of your wing, this is something that you can't change, but well, at least in the normal terms, you can increase the surface area by lowering your flaps and stuff. But in a normal sense, when we're talking about the wing, generally we don't say that you can increase its surface area, except for the flaps thing, which does. So this is also usually a fixed number when you're calculating it. And so we can use this formula to calculate the total lift that can be created. Not that you need to know how to do this, but just know that that's where this comes from. And so we can use this to plot charts, which are useful to us. So on this chart, there's a lot of stuff, but basically here in the bottom, we'll have our angle of attack. So from 0 all the way to whatever our stall angle of attack will be. And then on the left side here, we have our coefficient of drag, which we'll talk about in a second. And then we have the coefficient of lift here in red. And then we'll have our lift over drag, this ratio. And so we can trace these lines. So this red line here, this CL max, is going to be reading off of this chart over here. So this is our coefficient of lift number, if you will. And so as we increase this coefficient of lift, we can see how it affects the other things here. So for instance, we have this green curve here. And this green curve indicates how the lift to drag ratio is correlated with the the coefficient of drag and the coefficient of lift. And so as we can see, we increase the lift over drag number, so this ratio, and we reach this point, which is the L over D max. And this number is also called the best glide speed. And we use this number for engine out scenarios and stuff like that. So when you want to fly the farthest with no engine, that's what this number is for. And eventually, on the other end of this, with this angle of attack increase, we will we'll get to the point where we can't create any more lift, and then we'll stall. So yeah, I wouldn't worry about this chart as much. There's another chart that we'll see in a second. I think, I'm not sure if I put it in here or not, but basically the main idea here is this angle of attack increase versus our lift over drag number. And seeing that as we increase this angle of attack, we get to a point where we are minimizing our drag and we're maximizing our lift. And that point is called the L over D max. And that's our best glide speed. And then eventually we reach the critical angle of attack, which in this case is like, I don't know, 19.5 degrees or something. So that's basically all you have to know from that graph. Now we're going to talk about drag. So drag, we briefly touched on the types of drag, but now we're going to talk more in depth about what they are and how they happen. So there are two main categories for drag. That's the parasite drag and the induced drag. And the parasite drag is split into three more categories beyond just the overarching parasite drag part. So we have the form drag, the interference drag, and the skin friction drag. And we'll talk about all three of those here in the next slide. And then we also have the induced drag, which is caused by the creation of lift. So first, let's talk about form drag. So form drag is a type of parasite drag, and this is caused primarily by the shape of the object that the air is flowing around. So like we see on this chart here on the side, a plate is not very aerodynamic. It is very inefficient. As we move to more round objects like a sphere, we get more aerodynamically efficient, but we still have a lot of turbulence. If we have this sphere with this kind of fairing behind it where it tapers off, we get more efficient. We still have some turbulence. And then finally, move to this very efficient wing-like shape. And this is oftentimes what you'll see on some smaller aircraft. They'll have these wing fairings if they can't retract their landing gear. And this helps reduce the total drag that is created by this object that's sticking out from the aircraft. Antennas, wheels, flight surfaces, your hand sticking out the window, these all create this form drag. And so in order to reduce it, all you have to do is just make that shape more aerodynamic. And so as velocity increases, this type of drag increases as well. And so, which makes sense. I mean, if you've ever stuck your hand out the window while you're driving, it's a lot harder to keep it in one place while you're driving very fast compared to when you're driving slow. So just kind of think about it like that. Next type is this interference drag. And interference drag is a little bit harder to define, but basically it is the point where two airflows meet. So you have the wing of the aircraft and the air is flowing over that in one direction. And then, it connects to the aircraft at some point, the wing root. And this point, usually the air is flowing sometimes 90 degrees different from it. And this causes the air to mix, and it causes this drag to form. And so this turbulence that's created by this mixing of air causes a drag increase. And so sometimes you can minimize this, through reducing this angle or whatever. But just know that, it's this mixture of separate airstreams that causes this type of drag. And again, as velocity increases, your interference drag will also increase. And then the final type of parasite drag is going to be the skin friction drag, which is caused by the roughness of whatever your aircraft surface is. So if it has a lot of rivets that stick out, or if it has a lot of rough patches for whatever reason, those cause drag, and it causes the air to move less smoothly over the surface, and it creates turbulence. And so the best way to kind of take care of this problem usually is just in the manufacturing process. So, using flush mount rivets, smoother paint finishes, washing your aircraft. That's something we did almost every 2 weeks, our flight school, and waxing the aircraft as well. Also help in making sure that the aircraft is as smooth as possible and reducing the skin friction drag that's created by it. So, and then the other type of drag, induced drag, is caused by the creation of lift. And induced drag is caused by the same thing that creates wingtip vortices. So you have the air moving faster over the top of the wing than the bottom of the wing, and so you have this increase in decrease in pressure, and this causes the air from underneath to want to flow towards that area where it can, and so it does that around the wingtips. And so, like it shows in this diagram here, you get this circulating air that's flowing from the underside of the wing up to the top side of the wing, and then it has to continue around, and it creates this spiral pattern behind your aircraft. And this flow from lower or higher pressure to lower pressure does create some drag. And so, like it says, this downwash that's created, the lift vector from that points away from the aircraft. And so instead of getting the lift from that, you're getting this drag component. And this is inherent in all aircraft. There are some things you can do to mitigate this. I don't know if you've ever seen commercial aircraft that have things that stick out from the wings, like up and down. Winglets and sharklets are what they're called. And their job is to get in the way and make it harder for this to happen. And they do a pretty good job of mitigating that flow, but they don't stop it completely. And so this is just inherent with the creation of lift. So that's just something to keep an eye out for. So like lift, we have this formula for drag. So the formula is pretty much the same. We just replace the coefficient of lift with the coefficient of drag. So the coefficient of drag is the ratio of drag pressure to dynamic pressure. And so this is a calculated number. And we put that in the formula, and we can see that as air density increases, just like lift, drag increases as well proportionally. And then as our velocity increases, our total drag also increases. And then as we have this bigger surface area, we also create more drag. So here's the graph I was kind of getting at earlier. It's a little bit more simplified than the one that was in the lift section. But we basically have two axes. So we have the drag and the airspeed. So as velocity increases, our parasite drag increases. So, this things sticking out from the aircraft, the skin friction, the interference drag, all those increase with airspeed. And so we can see that curve here. And then our induced drag actually decreases with airspeed. So the faster we go, the less wingtip vortices are created. And so they're mostly created when the aircraft is really slow, especially when they're heavy. And so that's where we see the maximum induced drag And as we get faster, it will decrease. But there's this intersection point between the parasite and induced drag. And this point, which is this minimum drag spot, is the L over D max point. So this is the best glide speed that we saw on the other slide. So this graph is just an easier way, I think, of visualizing the L over D max concept. So best glide is the intersection point where we have the minimized induced drag and the minimized parasite drag. All right. Weight is obviously the force created by the pull of the earth on the aircraft. The weight vector always points down towards the earth. And this point where this weight vector comes from is the center of gravity of the aircraft. When the center of gravity of the aircraft is forward of the center of pressure or lift, it's that point where the aircraft is producing most of its lift, the aircraft is going to want to pitch down. This kind of makes sense if you think about it. If you have something really heavy, and think of the center of pressure as kind of like this, this tilting point, then, you know, if you increase the amount of weight on the front end of this fulcrum point, then it's going to want to point down. Then if you have, weight in the back of the aircraft, then it's going to want to pitch up. And so hopefully that makes some sense. Yeah, and like I said, the weight vector points towards the center of the earth no matter what. So thrust, this last force, is the force that counteracts our drag. This can be created as either a pulling or a pushing force, depending on the aircraft. So, a Cessna is going to have this pulling propeller that's going to pull you through the air, and then a jet is going to have the pushing force where it's pushing you through the air with its jet engines. And in order to accelerate, you have to increase the amount of thrust that is produced in order to overcome the extra drag. And so in order to, change altitude or change airspeed, you have to increase the amount of thrust that is produced in that aircraft. So it can either be done by increasing the RPM of the engine, or it can be done if you're in a variable pitch propeller aircraft by increasing the blade angle of the propeller and creating more thrust by that. And so, you need to increase that thrust if you want to accelerate and overcome the drag. So I guess I should mention that this point as well. If your thrust is increased and your angle of attack stays the same, so you increase your velocity essentially, but you don't change your angle, the aircraft is going to want to climb. This is just inherent to the fact that you're causing the aircraft to move faster, and so the aircraft is going to produce lift more efficiently. Without changing that AOA, that lift vector is going to increase and your aircraft will climb. If you want to stay at the same flight level and you want to increase your velocity, you have to pitch the nose down in order to counteract that. All right, so we talked about wingtip vortices very briefly. Now we're going to talk a little bit more about their hazards and some other stuff. So wingtip vortices are created by this equalizing of pressure. So the flow from the bottom of the wing to the top of the wing, and it occurs around the wingtip. And all aircraft create these. Some are just more dangerous than others. So large aircraft are particularly dangerous to small aircraft. Even really large aircraft like the Airbus A380 is particularly dangerous to even large aircraft like the 737. So these can be very dangerous. They can flip your aircraft over. They can, cause you to change altitude very quickly. It can cause the loss of lift. They are pretty dangerous. So they're most dangerous, though, when the aircraft is heavy, clean, and slow. And that's something to remember for the FAA exam. Heavy, clean, and slow. So when they're taking off and they've just lifted up their landing gear and their flaps, and they're not moving very fast, and they're heavily weighted down by all the fuel and people on board, that's when they create the most amount of wingtip vortices, or the strongest wingtip vortices.
When you say clean, do you literally mean clean, like the aircraft has been polished and whatnot?
Well, yeah, that too. But no, what it's referring to is actually the state of the aircraft. So the wheels are up, the flaps are up, nothing's hanging out, the spoilers are down,
Okay.
that stuff. So yeah, so it's configured for basically, it's getting configured for cruising speed basically, but it's not there yet.
Okay.
So yeah. So
Yeah, I was about to be impressed if literally the surface area of the aircraft made that big of a difference.
Yeah, no. Yeah. So yeah, heavy, clean, and slow is the most dangerous. So most of the time you won't encounter these if you're just flying around, but you will encounter them if you're landing or departing behind large aircraft, and they're heavy, clean, and slow. Oftentimes it won't be clean, but that's just what the FAA wants. So they'll probably be heavy, dirty, and slow, which is, I guess, the second worst. So they'll be landing, they'll have their gear down, their flaps down. They'll be really slow, and they'll probably be heavy. And these wingtip vortices will be very strong coming off the wingtips. Wake turbulence, which is what these are, sink towards the ground and then they move outward. So if you can kind of imagine them falling down behind the aircraft, and then once they hit the ground, they have to dissipate outwards, unless there's wind present, in which case they won't. And so the most dangerous type of wind for these wake turbulence is going to be these kind of winds that are pointing from the back side of your aircraft, or what we call quartering tailwinds. So they're coming from the back left or right side of your aircraft. And what that'll do is it will pin this wingtip vortice, or this wake turbulence, onto the runway for extended periods of time. And so you end up with this wake turbulence just sitting right in the middle of the runway, instead of moving out to the side. And so if you get caught in that, then bad things could happen. In general, though, wake turbulence usually dissipates within 3 to 5 minutes. So if you just wait that time, you can avoid it safely. The other thing you can do is you could try and time your takeoff and landing in such a way that you avoid them altogether. So if you don't have time to wait, you're on final approach and the aircraft in front of you just landed and the tower tells you, you have cleared to land, caution wake turbulence. You can do a couple of things. So you could wait, but that's probably not advised at busy airports. So what you can do is you can look where they land and you can look where they touch down. And oftentimes, at least on a good day, you can see kind of the smoke come up from heavy aircraft when they land, if you've ever seen that. And that's their touchdown point. And whenever they touch down like that, that's when the wake ends. So they're no longer producing enough lift. They create their flight, and so the wake turbulence stops and is no longer created beyond that. So if you watch for that smoke puff, then that's where it stopped. And then all you have to do is just touch down after that spot, barring any winds, of course. If it's particularly windy from behind, which I'm not sure why you'd be landing with a tailwind, then you should probably shoot for a little bit further down the runway. But in general, they'll dissipate behind you. So as long as you land after that touchdown point, you should be fine. So just aim for that point a little bit before that, or not before that, a little bit after that, and you'll avoid them. Same thing with takeoff. If you watch where they rotate, they actually take off the ground. As long as you rotate and take off before that point, then you should be fine. You won't hit those wingtip vortices. The one caveat to that, of course, is that you can't outclimb most of these airplanes. So at least in a smaller aircraft, you can't. And so you'll have to turn off of the course eventually. Otherwise, you will intersect them and, you get some turbulence. But so yeah, so those are some things you can do to avoid the wake turbulence. Any questions on that stuff that we just talked about? All right. Well, if you think of anything, let me know, and I'll try to answer that. Next week, we'll just continue talking about this stuff. Chapter 5 is kind of a longer one, so it'll probably take us next week to get through it. But yeah, we'll talk about flight performance and stuff. So should be fun. All right. I'll see everybody next week.